Welcome to Part 4 of Topic 2 in the Mate 210 lecture notes. Recall that when we have two atoms bonded together, there's an energy well that's created between the two atoms. And that energy well records the energy of the bond as a function of the distance between the atoms. And that there's a neutral distance, or 2 times the radius of the atoms, where the energy is at the lowest possible value. What's important about this curve is that it's not symmetrical, that the energy goes up faster as we try to push the atoms together and doesn't go up nearly as fast when we try to pull them apart. Well, that asymmetry is what explains the tendency of materials to expand when heated. And as we pointed out before, there's a relationship between the bond strength, or in this case the Young's modulus, and the thermal expansion coefficient of the material. As the Young's modulus goes up and the bonds get stronger, the energy well gets deeper and more symmetrical, and so we get lower thermal expansion coefficient. Let's take a look at how that happens exactly. First of all, what is thermal expansion? If I take a sample of length L and I heat it with heating coils, as the temperature increases, you'll get a thermal strain that increases proportionally, and the slope of this line is alpha, where alpha stands for the coefficient of thermal expansion. We can write the equation for the coefficient of thermal expansion as the change in length over the original length, or the thermal strain, divided by the change in temperature. Now, some materials have high alpha values and some materials have low alpha values. Materials with low alpha values tend to have very strong bonds, which means they have deep energy wells that are very symmetrical in shape. Because they're symmetrical, as the atom is heated from absolute zero, which is the bottom of the energy well, to higher and higher temperatures, the atoms oscillate back and forth between the two sides of the energy well, but the neutral or average position between that vibration, those vibrating points, doesn't increase very much at all. Whereas for a weakly bonded material with a much more shallow energy curve, the curve is going to be non-symmetrical, so that as the thermal energy increases from T equals 0 Kelvin to T1 to T2 and so on, we see that the average position of the atom, or the length of the bond, increases gradually with time, or with temperature I should say. So this leads our material to have a high thermal coefficient of expansion. The average bond length increases dramatically as temperature increases, and again a strongly bonded material has a low coefficient of thermal expansion because of the tendency to have deep symmetrical energy wells and strong bonds. This is an example of unconstrained thermal expansion, where the ends of the bar are able to expand as much as they want. So there's lots of strain but no stress present in this situation. But what if the ends couldn't expand as they wanted? Then we'd have something called constrained thermal expansion. And this is a classic picture from the 1940s showing what happens when the rails thermally expanded, but because they were connected to one another, they couldn't expand any further, and eventually the rails themselves warped into these bizarre shapes due to thermal expansion. The same thing happens to your cookie pan when you bake cookies on a pan. It heats up in the oven. When you take it out, it's warped and twisted. That's because of thermal expansion, or constrained thermal expansion. What's important about this is that the thermal expansion acting on the material will cause stress in the material. And that stress is given by this equation. The stress sigma equals E, the elastic modulus, times the difference in thermal expansion between the constrained and unconstrained material, times delta T. So if we had a plastic coating or a paint coating on top of a substrate, the coating can't expand as much as it wants to. So it experiences a stress at the interface between the paint and the substrate. And that stress is equal to this equation.